That's it. Right. The Daniell cell is a commonly referred to cell, quite, I guess, foundation reaction in the context of electrochemical cells, where we have zinc and copper. So again, like I said before, the zinc would be in a zinc solution, which could be a zinc nitrate, for example. And the copper is also going to be in a copper solution. So that's our two combinations, the zinc with the zinc ions and the copper with the copper ions. The thing we have to do next is look at our electrochemical series and work out which one's going to be oxidized and which one's going to be reduced. So can you have a look at your ECS and tell me which one you think is going to be oxidized? Yeah, the zinc is actually oxidized because if we look at where they sit, the copper half equation, the copper Cu2 plus ion is a stronger oxidizer than the zinc 2 plus ion, isn't it? And so with this combination, it's this one that's going to react with this one. It's the copper ion that will react with the zinc metal. We need to have the other two present, but these ones are our reacting species. So the zinc is being oxidized. That means that my anode must be zinc. And I'll be producing zinc ions in this solution. Okay, that's the oxidation half equation. And the copper electrode must be this one. So the zinc is the anode, has a negative charge. The copper is the cathode, has a positive charge. And the copper ions are being reduced. So we've got copper nitrate in solution. And Cu2 plus 2E minus gives us Cu solid. Okay, so, and we've got our nitrate ions, and in this case we'll have potassium ions, but it doesn't matter. It could be sodium ions as well. And now we're going to be looking at the values on our electrochemical series on your formula sheets. See what is listed as the voltage for each of these half equations. So what's the number next to the copper half equation?
Positive 0.34.
Positive 0.34. And what's the value next to the zinc?
Negative 0.76.
Okay. Now these values are relative to the hydrogen half equation. If you have a look on your formula sheets, you'll see that that has a value of 0. That doesn't mean that no voltage is generated if you use the hydrogen half equation. It just means that all the others are measured against it. Okay? And so how we work out the voltage that can be generated by this half cell, 1 molar solutions, is by working out the difference between these values. You can add them together. If there's, I guess, 2 ways of thinking of it. Just look at the difference between them. And because this one's a positive and this one's a negative, they're straddling that hydrogen half equation. So you're going to add the 2 numbers together. The other way you can think of it is you reverse the sign for the oxidation half equation. Because this reaction is going in this direction, then we have to reverse the sign. So this would then be positive 0.76. And this one is in already, the reduction half equation is in the correct direction, and so I can then add that on. Which is going to be what, 1.10 volts? Is that right? Yeah. Okay, so what this is indicating is that we change the sign for oxidation. Okay, so if that means that the oxidation has a positive value, then it will be a subtraction. Okay, so sometimes if you're right up in the top of the electrochemical series, the oxidation half equation can also be written out. It could be positive there. And we have some other shorthand notation that we need to look at. Now, if we want to just represent a half cell, the most oxidized species is listed first. Which would mean that this one is zinc 2+, and then a line to separate, and then the zinc solid. Okay, and then for our copper half cell, it would be Cu2+. Cu. Okay, so we're just writing the most oxidized species first that's involved in the reaction. We don't care about anything that's not involved in the reaction. But this is a little bit different to when you're writing out the whole equation, which is a little bit confusing. So for the shorthand for the full reaction, then we're looking at what's happening left to right. So I'm starting with zinc. Then, which is being oxidized to zinc 2+. A double line here represents the salt bridge. And then we see what's happening next, and that is that the Cu2+ is being reduced to copper. Okay, so we're basically writing it left to right. This is being oxidized to this, and this is being reduced to that. All right, which is different to this half cell notation. So questions might give you this half cell notation so that they're not giving you the clue as to which one's going to be oxidized and which one's going to be reduced, so that you have to work that out yourself. Now, not all reactions have the metal for the electrodes. For example, if I wanted to oxidize Fe2+ to Fe3+, well, I don't have an electrode. I can't use Fe, an ion electrode, because I want to oxidize the ions that are in solution. And in that case, I would then need to use an inert electrode. our inert electrodes are either carbon, as in graphite, or platinum. So if I swap this reaction around to show you what I mean, to oxidize the Fe2 plus to Fe3 plus, that's obviously going to happen at the anode, in which case my anode would then, say, become carbon. Just need a whiteboard marker that will actually work. Fe3 plus will come off. Fe2 plus goes on. My oxidation equation would then be Fe2 plus goes to Fe3 plus an electron. Does that make sense? So is that all right, that all I've done is I've swapped out the metal electrode for an inert, in this case I've represented it as carbon electrode, so that oxidation can still occur. My half cell then would be Fe3 plus Fe2 plus. And my shorthand notation means that I now have to indicate that I'm using an inert electrode. And so I write that first. And then what's happening? I'm oxidizing the Fe2 plus to Fe3 plus. Okay. And then the rest is the same. But the inert electrodes bookend. Okay, so if I used an inert electrode for my reduction half cell, it would be on the end here. If your reagent is, for example, acidified permanganate, you need to include the hydrogen ion when you're writing that. So you'd have the H plus with a comma, like that. Okay, so if it's acidified, don't forget the hydrogen ion. Same with acidified dichromate. Any questions? No? How about we just do one little last look here? What would happen then if, what's the equation here for the oxidation of the Fe2 plus? What's its E0 value? Fe2 plus to Fe3 plus. Sorry? Positive point.
0.77. Your concern, the other is going to be.
Yeah, we have a problem here. It's above copper. Okay, so that won't work. What we need is we're going to react it with silver. All right, we've right, so what are our two half equations then? What's this one?
The silver is yeah, 0.
And what's this one? It was 0.77. So remember, if we change the signs, then that would be 0.80 subtract 0.77, 0.03 volts. Is that right? All right. I think we've covered everything now.
By Fe reaction, Fe2 plus Fe3 plus an electron. Gosh, what should have got?
Yeah, I'm just writing them out as the reduction half equations on the that are on here, so you can look and see what value they are. That way you can see that we need to change the sign for this one, because this is the oxidation reaction that's going in this direction.
So it's going backwards, so you change the sign.
This reaction goes backwards, and so we have to change the sign.